So thanks everyone for being here. I will start with something about who I am so that you know what you can expect about the way I talk. I'm a passionate software engineer. That's the thing for this talk. And things I worked on is I started with telecom switching stations, then JIT compilers, the Mono project, and then V8 in Google. I worked with this a lot, 7 years something. Then game engines, Unity 3D, I've been working also there. I did the interactive collaborative VR on the web when it wasn't a thing. When Facebook couldn't monetize that, we stayed alive something like 8 years. Then we failed, that's fine. And then, meanwhile, I learned Rust, and then I worked on distributed systems and blockchains in Rust, and currently, operational research, algorithms, vehicle routing, mostly in Rust. Talk outline. Our own Rust project, this is the thing I do in my day job, the thing I'm talking about. How it went, why we did it, and how you can do it to use Rust in your company. What does it mean? And the talk will touch a lot of things. I'll be very fast, sorry. Many of the single things I'll say could be worth an entire talk. I did it this way because this is about Rust, and I'm saying a lot of things that then will be relevant because Rust here. So just try to follow this and let's see how it goes. First of all, the workplace, what we do. And I've been there since September 2020, but a bit of history. In 2009, there was an Italian company that was born, a small startup, Viamente, that was selling as a product routing as a service. What does it mean? If you are a company whose core business is delivery of field services or something like that, and you need to optimize the routes, but since your core business is not IT, you cannot build an algorithm to optimize them. You essentially buy our service. And we have two products, Routing Engine, which is a routing algorithm as a service. So if your ERP, your managing software is good enough and you can customize it to talk to our service, your software can produce the description of the problem, like I have this vehicle, this delivery, this delivery, this delivery, sends a JSON blob to ours, and ours replies with a JSON blob that are all the routes. Now, if you don't have the ability to do this, for whatever reason, we also have some kind of an ERP specialized for routing. So it's a UI on the web. You can define there your territories, your vehicles, your drivers, your deliveries, all the constraints and everything, and then you push a button and you have the plans, and you can visualize the plans, you can modify them, then you can check if your modifications introduced violations, and then when the time comes, you can act them live, following vehicles real time with GPS, see if everything goes right, and if something goes wrong, you can do live replanning with the algorithm. So this is the thing this company, Viamente, was selling. Then, in August 2012, WorkWave, which is a big US-based software company, now we are 1,000 something, so big, that kind of big, acquired Viamente because WorkWave does software used to run industries like ERPs and so on, very vertical ERPs, and they integrated this planning capability inside all the WorkWave products where this is relevant. So now the Italian team of WorkWave still maintains the separated products, the standalone products, and provides this internal service to all the other pieces of software of the big company. This is to give you the frame, what we do, how it is structured. When there was the acquisition, there was a worldwide growth, and over time, lots of new features. And in January 2020, the global pandemic wreaked havoc on the planet, but for this company, it was an explosive growth because all delivery customers had larger problems because pandemic. And then the algorithm performance was suffering because of the larger problems. They figured out this is going to become a big deal. And this is essentially where I started here. I was hired as an algorithm engineer to fix performance issue, make the system scale, and yes, implementing features. This is the way it went. So to make you understand how this is structured so that you'll see how Rust played a role there then. The architecture of the routing engine, which is the service, starts with the architecture of a single server. There is a front end, Nginx as usual, and then a main process written in Java that is essentially the thing that does everything is the monolith. And then there are geographical services which are installed internal on the same machine because we need to rely on them. And they are the pieces of software that we bought. We didn't write them. We buy the licenses and we install them on premise to compute essentially the physical routes, like what it takes from going from point A to point B. How much is it long? How long does it, sorry, in miles? How long does it take in time? If there is traffic, no traffic, kind of vehicle, different driving profiles, whatever. All these kind of problems are solved by this software that we bought. And then the algorithm processes. The algorithm is written in C++, and the main process, the Java one, each time a computation needs to be performed, saves on disk a description in a horrible in-house format that it was built so that the parser was easy to write in C++ on the fly, like with minimal effort for the C++ programmers. And essentially, it writes the description, runs the child process, and when the process is done, finds the result on disk, and it's done. And that's it. Essentially, the performance critical thing is a C++ executable, and all the rest is all this architecture. Of course, there is DB shared file system. And the whole system, the cluster, is a load balancer that balances onto small servers that if they decide, oh, I'm small enough, the problem is small enough, I can do it, they just do it. Or they relay to large servers that do the same thing. And then there is the DB and the shared FS. This is the cluster of the routing engine. So a routing engine deployment is all of these machines. And now about the algorithm itself. It has been mostly written by an operational research professor of the university in Milan that works part-time for university and us, which is amazing. I mean, this man is a genius in algorithms. It's about that amount of lines of code, 75,000. I just counted them last week. But it's very simple C++, just C with classes. It's nothing fancy. And it has lots of features. By lots, I mean really a lot, because over time, we were trying to cope with everything that the customers could need. And just to make you laugh a bit, imagine a customer who is actually moving people, like organizing routes of on-demand buses. But for religious reasons, the first to hop on needs to be male, the last to drop off needs to be male, and no woman can sit alone on the bus at all times. So the algorithm needs to take this into account, otherwise the customer wouldn't be able to schedule the vehicle. Or think you're moving livestock, like a group of either sheep or pigs or whatever. And there's a problem, that there is a category of animals that can infect another, but not vice versa. So if you load them and unload them in the wrong order, essentially you will need to sanitize the vehicle, which will make you lose a lot of time. So the algorithm needs to keep these ordering constraints into account. These are the two hilarious ones. All the other ones are like costs, delays, configurations, affinity, anti-affinity, vehicle, driver, poses, mandatory poses, temporary. It's incredible. And the implementation is a jungle of linked lists, because the thought 15 years ago when this code base was started was I allocate everything on the start and then I move pointers around and it's understandable, the initial approach. It's just a nightmare. And the problem is technical debt. This code base is really 15 years old. And again, it started like, if anything can be a mutable shared global, it is. Because there is only one plan that the algorithm is going to compute, and so that's it. And 0 unit tests, because you know C++. And there is a lack of properly designed abstractions. There was never really a significant refactoring because, well, time pressure. Time pressure builds technical debt, we know. And the result is that the code base is brittle. So when you touch something there, you always risk to break something because the invariants are not really written down. If you invoke function A, then you need to invoke function B and C, otherwise the invariants aren't met, but there is nothing enforcing that. And if you have not worked on that for years, you don't know. And so you just pretend you are walking on tiptoes, trying not to break anything, and you are actually like the elephant in the room that breaks everything left and right and you don't know it. And that's working on this algorithm is this. And now the performance problems of the algorithm. They happen when you handle larger problems. The algorithm requires full edge matrices. So if there are 100 locations, it needs to have a matrix 100 times 100 with all the distances, all the times and everything, so that it can do attempts to build the routes. Which it makes perfect sense. But the problem is that if the locations are 20,000, the matrix grows quadratically, and this is a problem. This is really a problem. Now, linked lists are not cache friendly. At some point when I was hired, I just started experimenting and seeing things, and I used the perf, the profiler, the hardware profiler for cache misses, and I was like, I couldn't believe it. It was just executing from RAM directly. Because what it is, that's okay. And then there is another problem. The way the algorithm works, it tries to find a feasible solution, and then it tries to improve it by permutating things. That's the only way to do an algorithm like this at this scale with this kind of complexity. But the search space for possible exchanges inter-route from one route to another, when the problem grows quadratically with the size of the problem. And again, there's nothing you can really do about that. It's the way it's designed, and that's a scalability issue. Okay, now I've been talking about the C++ thing. What about Rust? I accepted this job knowing that it had the potential to be a C++ only job, while I actually work at a Rust job. So that this has the potential to work right. It did. So initially, I was doing experiments analyzing problems. So I was examining the performance of the algorithm and also understanding the problems that we have, how they are done, what kind of characteristics do they have. Are they big, small, many vehicles, many locations, many constraints? And I essentially downloaded 3 months of data, half a terabyte of things, and I was analyzing this thing in every possible way. So I needed tools, and the tools had to be fast. So I just built the tools in Rust because it made sense. It was not code that was meant to go in production. It was just tooling. Then management calls, we really need to scale now. And there was an ongoing plan for scaling up. And it was to split larger problems into smaller problems, then solving the smaller subproblems. Since the complexity is quadratical, this helps a lot. And then producing a unified solution, adjusting things in the middle. I'm not getting into this because this talk would explode. And the splitter was mostly done when I was hired. So I had this time for experimenting and understanding, but then we said, okay, we need to do this thing, period. So how the splitter works, so that you get an idea. Suppose you have a large problem, so a central warehouse, 4 vehicles and things to do around. You split it, and then each subproblem can be solved one at a time, possibly in parallel, and then the result is merged into a single problem. This is the thing that the new algorithm should do. And there would be different implementation approaches. The one that was planned before I was hired was the minimal change. Implement the C++ servers orchestrators in process. So it was already C++ code, the splitter, but you need an orchestrator that invokes the splitter, then all the subproblems, merges, split, all those things. They still had to be done. And the initial plan was to do everything in C++ in process. Now, I came in and I said, OK, we could use Rust with minimal change, like implement the Rust solver orchestrator in Rust, but make it in process into the C++ algorithm. That would have been an option. Actually, what I opted for was the Rust with minimal risk. So the Rust solver orchestrator out of process. I did this because I really wanted to solve subproblems concurrently and touch that code base to allow multiple problems in memory concurrently, in my opinion, would have been a total nightmare. And so I just decided, let's keep this thing one algorithm per process, and I make another parent process that does the thing. So now we have a new component. We call it the runner, because what it does is running the splitter and the algorithms. And thanks to the exploratory phase, there was Rust code that could parse and write problems in the format desired by the algorithm. It was already there. I had already written it. And so we had this head start. We could really easily implement the runner in Rust. And the runner mimics the underlying algo process so that the routing engine can just pretend that the runner is the algorithm. So there is minimal change for the routing engine. The Java process invokes a sub-process. This child process happens to be the runner instead of the algorithm. I try to mimic everything so that the impact is minimal. This was just the most sensible thing to do design-wise. And technical highlights, the runner tries to stay out of the way, it's very thin wrapper, almost zero CPU time because it's just everything is async. Run processes do things, it's very simple. It's also non-trivial for a lot of reasons because the child process are a lot. They organize it in stages. First do the splitting, then solve the sub-problems, then do the merging, invoke the algorithm on the merging. And then it has to process the std-out of everything and merge all the std-out in a single stream, exposing that stream to the routing engine. So the routing engine sees the same std-out that would have been produced by a single algorithm in real time. And also waits to the std-ins of the child processes to control them like the routing engine could have done with a single process, but for each of them for anything that needs to be done. Collect partial solution in real time, because they have this thing that if the customer wants a solution now and the algorithm is still running, the routing engine can just go on disk and see if there is a temporary one, which is valid, and retrieve it. So the runner needs to take all the sub-partial solution, merge them in real time, provide the temporary solution, and all sort of error and corner cases. So it's simple in principle. In practice, it's not so simple, but it worked. So far, so good. We have Rust code in production. It's working flawlessly. This project went really well. So, success. Then management comes knocking again, and what do they ask? We need to scale. I say, what? But didn't we implement the runner to scale? Yes, but that was scaling up. Now we need to scale out. So just to, you should know, but just to visualize. Scaling up, you have a small problem, you use a small machine. You have a bigger problem, you use a bigger machine. And so on, you take bigger and bigger machines scaling up. While scaling out means you have a few problems, you use a few machines. And more problems means more machines. And so on. This is scaling out. This is a totally different thing. So logistical computations at scale, what does it really mean? At what scale are we doing this? So in production, we have about 220,000 requests per day in normal working days. There have been days with 400,000, but anyway, there are spikes. And this means a total of about 800,000 computations per day for the algorithm, because some customer requests are actually requesting several alternate computations and scenarios in parallel. So we have this amount of invocations, and problems can be anything from a small problem of a few milliseconds, just one vehicle and 15 deliveries, to huge things of literally thousands of, well, thousands maybe not, but 500 vehicles, 20,000 deliveries spread over 7 days when the algorithm has to match and match. And it takes something like 2 hours and a half to do something like that. And this is the scale. And about 40,000 vehicles worldwide depend on this. So they travel because this algorithm actually produces the routes. Then we have testing. Now, I pictured a very, let's say, bad proposition for this C++ piece of code, but we actually do care about quality a lot. So we don't have unit tests, but we do tests. And we have a pool. So we solve the problem with brute force. We have a pool of problems with every possible feature exercised in different ways, and they're about 180,000. And running this in the current testing infrastructure takes 1 week. And we don't make a bigger one because it's expensive. It's not dynamic because the algorithm is not dynamic yet. So, and then we have one public demo environment, but we'd like to have more, because sometimes one customer was something new, another was another new, and we would like to provide all of them independently to different pilot projects. Right now, we only have one. So the actual goal of this scalability project are to dynamically provision compute power, so we can afford more eventually, because normally we use less. To simplify deployments, so that now deployments mutate literally existing servers. They are fully automated and so on and so forth, but essentially they are machines that are provisioned where software is installed. So I don't really like it. Then allow more tests and experiments because we can scale also tests. Now testing is too slow. And creating deployments is also expensive. Live experiments are unfeasible right now. So how do we do the scaling? Well, you remember the routing engine architecture where everything was on every server? This architecture. Now let's take the most computational intensive thing, which is the algorithm processes. And we take this thing and we put this thing into an external service and make that scalable. And the plan over time is to take things off and make them scalable outside. So that's the thing. So now we have this new service to design. The design principle are, the DevOps is Kubernetes based, so that we get scalability out of that without thinking. You say, why Kubernetes? It's a big mess. Yes, it's a big mess, but it's also very powerful. And in terms of compute costs, it can be very convenient. Because if you are on a cloud provider, say AWS, by the way, we are on the AWS, but that's not really important. You can pay for flexibility. You can use ECS, the container engine, or you can use Lambda, or you can use those things. But in practice, if you do measurement, you are paying more for the compute power than if you rent your own EC2 machines. On Kubernetes, you are essentially renting bare EC2 machines and organizing your dynamic workload on top of them. If you use a thing that is called a Carpenter that dynamically provisions the machines for Kubernetes, essentially you have the best of both worlds. Because everything is dynamic, and the costs, you can even instruct Carpenter to use spot instances if you wanted and if you need, so that the prices use them lower. The point is, you do a couple of things. It works. It's a big gun to use, but in our case, it's really worth it. Now, in this thing, we have job queues. So when things arrived, they are put in queues. Because the problem is that these problems can be very big. So you cannot just make a simple server that replies synchronously. Because if the thing takes 2 hours, you cannot pick a server at random. You should pick an unloaded one. But at this point, if you make it queue-based, the unloaded ones will pick from the queues themselves. So it just scales naturally. So this is really the poster child for job queues. It just works well. Stateless components by design, which makes sense. Externally provisioned stateless services. And mostly the 12 factors, the basic design principles of a sane system. So the architecture of this new system is front ends, stateless, a bunch of them as much as needed. A fast store, which is ready for the queues and temporary data in general. So anything that is running, so a job that is running is represented there. So that if any part of the system needs to know, and that is the central state. So queues, and it's not really caching, because it's actually the live data, the live representation of the system. Then a slow store, say S3, for archiving. So when the thing is done, you put it there so that you have for reference and everything. And then worker nodes, lots of them, that take from the queues and process things. They run the algorithm, essentially, or the runner, because that's unchanged. This is the general architecture. There is also another dynamic process, the monitor, because the monitor is the thing that monitors things and decides how to scale the worker nodes. It's not mission critical in the sense that if it breaks and restarts, you just lose the capability of restarting new nodes for a while, let's say 5 seconds. You just don't care. It's not really a big deal. So it's a single point of failure, which is not really a failure. OK, how it went? It went very well. The issues we had were not related to Rust. We had, let's say, system issues like S3 write throughput. It was terrible because we needed to do a lot of small writes, and it is not engineered for that. So we ended up batching the writes into packets that we could then disassemble later. It's fine. We stumbled upon that. We thought it could work. We didn't. Fine. Then we also have a shared file system because, again, sometimes we want to write something immediately and be sure it is persisted. So we have this distributed file system that accepts these things, and then we bring them to S3 later. Then Redis I/O operations, there were too many of them. We just had to tune the thing, understand something. But again, the systemic things, not a problem. Then the problem of latency. Now, other internal components in Workwave that were using the service had big troubles because we increased the latency. I designed this thing with latency in mind. So sometimes the latency is just milliseconds, even less sometimes. I was obsessed with latency when I designed it. For some problems, Redis related, latency grew up a bit more. And the problem with latency is that if you are a system that uses this service at scale, the added latency means that the number of running jobs for you increases. So a 10-fold latency increase maybe means nothing for a customer if it is 1 millisecond or 10 milliseconds. But for that system, it means you can have, instead of 100 running jobs, 1,000 running jobs. So this caused internal problems. And to overcome the latency problem, I just noticed we had a steady stream of small requests that I just didn't notice could have been a problem. I designed the system to scale out for large problems because this is what I was asked to do. But in the end, we have something like 100 small requests per second. And this dominates the load completely. Now, those small things, the algorithm takes 1 millisecond to do. For them, just skip the queue. Use the normal strategy of having a pool of workers and ask them. So now the queues are still there as a fallback for the small problems, in the sense that if the workers are overloaded, and there is a protocol to understand it, it's quite simple. The front end takes the request, gives that to the worker. If a worker replies with a load balancer, an internal thing in Kubernetes, if there is a worker that replies, fine. If the worker that replies says, sorry, I'm full, it means that on average, the workers are full and the monitor should create more, but for some reason didn't do that fast enough. So that job goes into the queue, which means that the system is still fail-safe, nothing gets lost, everything works. There's nothing you can do if you don't have enough workers, so you have to queue them anyway at that point. Since we already had the queue system working, the change has been very, very simple. And there is ongoing work. We have a new algorithm strategy, which you call compact mode. Sorry, I want to check one thing. OK, we are on time. So there is a category of customers that work in what we call the green industry, not because it's sensible for the environment, but because it is, they work doing something like garden maintenance. And they do that at scale. They have lots of sub-customers, lots of things to do. And the routes for their vehicles need to be very compact, because if a serviceman goes into a neighborhood where there are 2 possible customers, and it mows the field of one, the garden of one, and not of the other one is really upset. So the idea is that if a vehicle goes in one neighborhood, it must do everything that must be done there. Sometimes the algorithm, for optimization reasons, didn't do that, because it was more convenient for cost-wise revenue or time or anything, do something in a region and then something in another region. Region, I mean really neighborhood. And so we had to change the behavior of the algorithm. But the problem is that the algorithm really is not so much location aware in terms of density of things. So we had to come up with a different piece of code. And we ended up doing a Rust component which preprocesses the input, inserting compactness hints for the algorithm. And why? Because implementing this complex algorithm inside the C++ code base would have been error-prone. So we have this thing. Other future plans, apart from matrices preprocessing. So another thing is, right now, the processing of the matrices is done in the routing engine servers. We need to pull it off everything. Also the GIS software, we have to pull it off and deploy separately. And then the computation of the matrices now is done by the Java code, pull it off, and do it at scale elsewhere. But apart from that, we intend to re-implement completely the inter-vehicle route permutation steps. Because of the scalability problem I described before, the logic that we use now is problematic because you have all the data structures of all the routes, and you try to do a permutation that moves one service from one route to another. You are essentially mutating the whole plan. So you need to do them one at a time, and you need to recompute the feasibility of the whole plan, so of all the mutated routes, fully. Since the constraints are nonlinear, this takes a lot of time. So the search space is large. The cost of the single operation is large. This is really the scalability bottleneck in the algorithm. This is the thing that must change. And now we have a different algorithm in mind, which if I described it here, it would be a problem because this would be the talk would grow too long. Maybe we will talk later if you want something about this. But what's important is that at this point, also thanks to the compactness-based algorithm, we have enough Rust building blocks that we can really prototype this thing in Rust without a huge cost. And at that point, the C++ algorithm would operate in single vehicle problems. So the idea is that you have a master algorithm that tries to allocate, with some logic, waypoints to vehicles, and then gives single vehicle routes to the algorithm to optimize, possibly all of them in parallel, which is a huge win. And then it gets the results with a few more data that we are designing, and this data is fed back into how it went, which points are problematic for one route, they cost that route too much, so they are candidates to be moved to others. And then this top-level algorithm moves waypoints around in bulk, and then reruns. This is, again, an iterative algorithm, like you always do. It has a lot of potential. And the idea is that when the C++ algorithm is reduced to a single route algorithm, a lot of the complexity goes away. So you can guess what happens next. It is feasible to actually rewrite it completely because it would need. So we also have new algorithms for the single route that would work even better. And OK, there is ongoing work. So this is things that will happen. And we have more future plans, by the way. The algo server architecture was actually very conservative. So I went by the book. I didn't want to take risks that were too big, because I was already introducing Rust. So for me, it was a risk. I didn't know what would happen. So I just went by the book. Stateful external services, like databases, Redis and S3 and everything, stateless things, everything works that way, and it worked. What I did not know is that Rust works so well. And so in practice, now I can consider a bolder design. Now, this is the architecture as it is now, with the monitor, the fast store, Redis, and the slow store S3. And essentially, Redis, it works very, very well, but it's a bit of a pain point because we have to pay for that. Like, for testing environments, we just fire up a pod with no real persistence because it's a testing environment. But in production, we need a proper fault-tolerant installation, which masters those replication, and that needs to be maintained. So we take a managed one, which we pay for, and it's a cost, and it's also partially a bottleneck. Now, the idea would be to change it. The change is not that big. Use a database, and a real normal database, MySQL. We already have them around for other reasons. Just for the state of the requests. That's not a big deal. A database can handle them fine. Also, the routing engine does it. So the state of the requests means a request is there, it is running, it is done. This is the result. That's it. So it's very simple. Redis has a lot more data because each worker has several state variables. In Redis, there is a lot of things, events, event collection. The idea is that all this information are already in the worker nodes. Why do we have to replicate them in Redis? We can, if a front end needs them, they can just go and ask them to the worker node. So the idea is that if the monitor, we enrich it a bit, it becomes a bit of a more of a point, but again, the state is on the DB. So if anything happens, it restarts immediately taking the state from the DB, the state of the queues. And the state of the system is in the worker nodes, because the ephemeral data is already there. If a worker node is working, the state is there. And if it's there, well, the state is not there, the worker is there, so what's the point? It should be deleted from Redis anyway in the old design. So if we make a point-to-point connection between each front end and each worker node and the monitor, I mean, it's a stellar connection. So everyone to the monitor, and that's it. The monitor can become a broker for requests when a front end needs ephemeral data. And given the performance that we have seen in Rust, this is actually feasible. This is not a risk. I would not have done this as first design because I was fearing it would have been a problem, but it's actually feasible. So this is something that will also happen in the future. Again, so far so good. Now I want to say Rust is not only unicorns and rainbows. Of course, there are a few pain points. They are the usual ones, literally. Async Rust can be tricky. It took me some time to actually wrap my head around it and understand things. Now I'm pretty expert, I can do things, but it took me months of struggling with things sometimes. And this is, I say it's normal, everybody says so, we experienced that. It is like that. Just an example, so you laugh a bit. Small digression, just a single spawn in Tokyo is like this. And you see those static trait bounds. What are they? Why are they like that? And the application is, you go from a Redis stream to a channel to a Tokyo stream. Essentially, you need to spawn a task that consumes from the Redis stream and writes into the channel so that you can use the Tokyo adapter to get a Tokyo stream out of the channel. That's, in my opinion, the sensible way of doing something like this. But the problem is that you are spawning this task. And there's this static lifetime. And the net result is that you cannot keep a reference to the Redis stream. You need to give the Redis stream to the task. That's just the only way. So you need to clone it. So you have more Redis connections, and the Redis pool is stressed more, and so on. And while understanding this, the question is, do F and output in this description of the spawn signature, do they need to live forever? And can you tell the difference between a static lifetime, and the tick static bound on the trait? Now, this is extra tricky. Now, the actual answer is the static lifetime. So the static declaration is static. Declared static lives forever. The static lifetime is a lifetime that potentially lives forever. But the static trait bound is, this thing can die. It's not a problem. It could live as long as the recipient wants, but eventually it will die. It's fine. But it cannot contain references that are not static. Now, this single thing, it's too hard. I mean, anyway, this was just a digression to say, when they say async Rust is tricky, yes, it is tricky. Back to Rust issues. The other one are just, our code base is like this. We have 60,000 lines of authored code that I wrote, and the dependency, we vendor them in Git so that the build system is deterministic, so I can see them. They are all in a directory. And when I counted the lines of code of my project, I was just blown away. I said, what's happening? And I said, oh, the dependencies. Those are the dependencies. So CI build times are slow. Caching is mandatory. Until I fixed the caching problem in the CI builds were a nightmare, something like 20 minutes something. Now they are 2-3 minutes in the normal builds, which is fine. But without a proper layer of Docker caching, Docker image caching, and really. And then, again, VS Code and Rust Analyzer at startup with all those lines of code. For me, restarting Visual VS Code is like, oh my. Okay, nothing bad. Because actually, there is the flip side, the strength. Rust in production is boring. Bugs, where are them? We don't know. Seriously. Somehow, the code of this project has been almost completely bug-free. And when there were bugs, there was analysis holes, literally. It was just incredible. You use the type system properly, and you are on Rails. Performance is stellar, really. The front ends, I was provisioning hardware for them, and then I was looking at what they were really using, and a single stupid pod with a few hundred megabytes could handle the whole production load just fine. And I just use 3 for redundancy because you have to, but just for that. Resource usage is minimal, and fearless concurrency is real. So in this thing, I spawn Tokyo tasks left and right. I can have hundreds of thousands of them running, and it just works, and I never had a single bug related to multi-threading, which if this had been C++, I just don't even want to think about it. So in this project, you say, why Rust? Well, the algorithm is performance critical. It is already implemented in C++. And we needed to build high-level code because the algorithm is complex, and also networking protocols, API persistence. But my goal was that the algo team should work on a single code base long term. And so this single code base is natural that it should be Rust, because at this point we can implement both the networking code and the high-level things and the algorithm all in the same language. It has a lot of potential. And as I said, it is very good at high performance and high level. This is really a strength of the language. What about management? So how did I get away with this? I was hired to work on a C++ project. I ended up working full-time in Rust. Suppose you want to introduce Rust in your workplace. This is something that could happen. What does it take? Well, it needs to make sense. This is the first thing. So Rust strengths must be relevant to your project and not just mildly. They need to be enough to justify the hassle. But the problem is that making sense is not enough. You need trust. Key point is that management trusted me. I was really thinking, they really did a leap of faith, because I just said, for me, this is the best thing to do. And they say, yes, go ahead and do it. And the point is building trust, because trust is a prerequisite. How do you make so that your managers trust you? Well, in my opinion, you should do well the very thing that you hate doing, predicting the future. As developers, we hate predicting the futures. We know it's unpredictable. We just don't want to give estimates. We know they are a joke. But the point is that they are needed. And in my opinion, in software development, being reliable, when for tens of times you say this is going to happen like this, and it happens, then you're building trust. That's a single thing. It's actually very, very simple. So building trust is a process, and if you think about it, it's perfectly normal, because it's like the scientific method. You don't know in advance if something is true or false. You run experiments, see results, and then if the results are consistent over time, you say, okay, this is a law, this is true. So it's being rational. This thing is just being rational. It's not emotional. Trust should be rational and not emotional, by the way. And so before somebody misunderstands what I'm saying, reliable is not perfect. I mean, I could be a reliable software engineer. I'm far from perfect as a human being and software engineer. Making mistakes is okay, it's fine, we are human. And thinking that someone is not reliable is okay, because sometimes people disattend your expectations, and rationally, you need to be prepared to cope with that. But making somebody feel bad because of a mistake is not okay. That's the thing. So the corollary is just spread love to everyone. You should not forget this. You don't start on a spread, you must be reliable, whatever. No. Being reliable is important, because trust is important, but just keep some sanity in your mind. So A healthy workplace is when you trust your managers and coworkers and they trust you, everything is fine. And if your workplace is not healthy, if there is no trust, believe me, technical issues like using Rust should be the least of your problems. So if you say, I cannot introduce Rust in my workplace because management doesn't trust me, the problem is not that you cannot introduce Rust in your workplace. That's not the problem you should try to solve. Recap, Rust is amazing. There are projects where it shines, maybe not all of them, of course, but there are some. And you build trust by being reliable. A healthy workplace is important, even more than the technology that you use. And that's it. Thanks.
Thank you, Massimiliano. So, what are your questions?
Hey, thank you very much for the talk. Did you have chance to talk to original implementer of the algorithm? Was the code commented? Like, how much trouble you had understanding it?
He still works with us, and the fact that he will or will not learn Rust is on the table, because he's a professor of operational research. His focus is on algorithm design, not necessarily writing code. For him personally, writing code is exciting because he's solving real-world problems, but annoying because it is writing code. And so it will be something that we will decide what will happen. Maybe he will learn Rust and actively participate in the development of the new algorithm versions. Maybe he will not and will work like an algorithm consultant, which would be anyway extremely valuable. Having a part-time algorithm consultant at that level is already amazing. It's just, we will decide. It's not really a big deal. There are other senior developers in the company that already learned Rust and are getting into the code base. So it's not that, because having a bus factor of 1 is a problem. The company knows. Right now, this thing has sort of a bus factor of 1, which is wrong, but we are acting for this. So essentially, developers from the other code bases, the other teams are growing so that these senior developers will have the time and the possibility to learn Rust and transition to this. And this is actually happening, and they are happy about it. So, but not necessarily the original writer, just because of his professional profile, which is not a software engineer. It's a professor of operational research. It's a different thing.
I'm also tempted to ask something about like feelings. I mean, did you feel stressed during that experience? Like, was there a moment when you kind of were not sure that this will land?
No. About the fact that Rust was a good thing and would have worked, I've been very, very confident, because every experiment said me so. I mean, this was not my first full-time Rust job, not the first time I used Rust, so I already had confidence in the language enough. And as you can see, also the introduction has been very step-by-step. First, external tooling, then a single process that runs other things. So it's just piece by piece. The funny thing about this project is that the incremental thing didn't happen in process in the C++ executable, but out of process with external components one at a time, which over time make the old code base irrelevant, but just over time. And this has been a conscious decision to minimize the code instability risks. I was thinking, if I put Rust inside there, and then there is a C++ bug, how do I debug this? Where do I point the finger? Where do I look for it? Because at that point, it's really hard. And I just decided to minimize that risk, to cut it out. That's it.
Thank you.
Questions? Here.
So you mentioned you didn't have any bugs once it got into production, apart from
more on the microphone, please. Sorry.
You mentioned that there weren't any bugs when it got into production, but you did have a couple where there were holes in the analysis. Could you elaborate on what those holes were?
Do you have a couple where? Repeat, please.
Sorry. You mentioned that there were bugs, a very small number of bugs in the production code, but only coming from where there were
analysis holes.
Yes.
Okay, the most silly source of analysis holes was the format of the input file for the algorithm. This is because that thing was really mimicking the in-memory structures of the algorithm with text files. So sometimes there is an integer that in principle is optional, but if inside the algorithm, if it is -1, it means it's not there, because you know C++. So in the text file, do you expect a -1, or do you expect the property not to be there? And it turns out that the algorithm expects the property to be there, mandatory, eventually with a -1 value. But in the small documentation that we wrote describing the thing was marked as optional. So inside the Rust data structure, it is an option of a value, because in principle, the property is optional. But the Rust data structure needs to mimic the file format as precisely as possible, because round tripping and everything. So it happened that at some point, I started receiving -1 from disk and writing no property to the algorithm, which is, okay, this is an analysis bug, because in principle, we should have known that the format had this property and so on and so forth. It's just a mess, seriously. This one was one of the most silly.
Questions? Questions? Anyone? No? Yeah. You want a hug?
You said spread love, so no, just maybe a little bit off topic, but I was thinking, just out of curiosity, if you incurred in some problems because, I mean, how do you split the inputs? Because you said that you.
Oh, so you're asking about the algorithm of the splitter?
Yeah, because I feel like if you split by vehicle, you can cut out some solutions.
No. So
okay.
The current splitter doesn't split by vehicle. It tries to split as less as possible while keeping the sub-problems manageable. So in a very big problem, like 20,000 and so on, the original algorithm can take something like 2 hours and a half. With the splitter, it takes something like 12, 13 minutes. Why? Because the sub-problems are smaller, so the quadratic effect does not kick in, so they are very, very fast. But the quality of the solution is not as good, because the algorithm doesn't have the full view. It optimizes locally, which means you don't want to make the sub-problems too small. Otherwise, the quality will suffer. You will have a very fast run with a very poor quality. So what the splitter does is look at the overall dimension, have a threshold for the size of the sub-problems, and use that as a measure for the number of sub-problems. Then there are all sorts of things, like geographical considerations first. Then where are the warehouses? Because sometimes you want to split by warehouse if there are more than one. Otherwise, you can imagine. Or affinity with vehicles and waypoints. Sometimes it can happen that you have one vehicle that can serve one waypoint in one region and another totally in another place. Now, what you need to do is to put all these waypoints in the same subproblem, even if geographically they are very sparse in the middle of others. And that's just the thing you have to do. So the splitter is actually a very, very tricky piece of code because of all these complications. But the key point is what's driving everything is the size of the subproblem.
Okay, thank you.
Any other question? Yes? No? Maybe? Questions? No? Okay. So, yeah, this is it. Thank you, Massimiliano. Massimiliano Mantione.
Thank you.
Mantione.